Now it's time to go to the real business, and I will just present a little Sebastian, even if I assume that everybody knows him. Professor Sebastian Geiger is Professor for Sustainable Geoenergy and Energy Simulation Chair at the Department of Geosciences and Engineering at Delft University. And before joining TU Delft, he worked for 16 years at Hierarchical University in Scotland, where he was an energy simulation, holding the energy simulation chair for 11 years and held several university management roles. Sebastian received his PhD from ETH Zurich and holds graduate and undergraduate degrees from Oregon State University in the US and University of Freiburg in Germany. In 2017, he received the Alfred Wegener Award from the European Association of Geosciences and Engineers. In 2020, he was elected as a Fellow of the Royal Society of Edinburgh, Scotland National Academy of Science and Letters, and in 2022 as a Fellow of the Royal Academy of Engineering in the UK. Sebastian graduated over 30 PhD students, supervised all 100 MSc Master of Science theses, and trained 12 postdoctoral researchers. Has published over 200 reviewed technical papers in conference proceedings or peer-reviewed journal, and edited one book. In this occasion, he will give a talk on modeling fracture in geoenergy application. I record everybody that the seminar is recorded and available on YouTube. And if you want to pose a question, you can just raise your hand with using the Zoom tool or use a question and answer. We normally ask to answer the question at the end, but if there is just a short clarification, it may be answered during the talk. I also give the announcement for the next GS webinar from Jeffrey Hyman on May 10, 2023, with the title Interplay of Multiple Scales in Fracture and Media of Flow and Transport Properties. So Sebastian, it's, the virtual floor is yours. Stop sharing.
Let me just get my presentation up and you should be able to see it.
Yes.
No, I hope so. Yes, so thank you very much, Luca. Thank you, Marcel. Thank you to the SIAM for inviting me to give this presentation. Before I do start, I would like to emphasize that the work I'm showing here isn't really my own work. Most of the work, if not all of the work, was done by a host of really talented PhD students whose pleasure and it was really privileged and honor to supervise them and work with them. And I hope I'm not going to forget mentioning all the PhD students at the right point in time when I talk about their work. So I was looking, when I was preparing the talk, I looked back at a talk I gave at the SIAM Geoscience conference in 2015 at Stanford University. And either the talk was so good that it was a repeat invitation, or it was so bad that you've forgotten all about it and you make the mistake to invite me to give it a talk twice now. We'll see, I'll let you judge that at the end of the presentation. But when I closed that talk at SIAM Geoscience in 2015 and talked about fractured reservoirs, so I've outlined there two opportunities where we can do more research. One is around geomechanics for fractured reservoirs, and one is to start thinking about how we can do uncertainty quantification, clustering, model ranking, robust optimization in the future. And what I'm going to present today is a little bit of the continuation of the theme around geomechanics, uncertainty quantification, clustering, and model ranking for fractured reservoirs. Now, before I go into the technical details, I want to spend a couple of minutes talking about the context. Why do we do the work that we do? And you see is from a plot from Our World in Data that shows the population growth since 1800 and then the forecast to 2100. At the moment, in 2023, we have about 7.8 billion people on the planet. That number is expected to grow to nearly 10 billion people by 2050, when most countries have agreed to reach their net zero targets. most of that population growth is going to come from the countries in Asia, Africa, and largely from countries that do not have access to affordable, secure, and sustainable energy at all. And what this sort of presents us with a fundamental challenge of tackling energy injustice. Again, this is a plot from Our World in Data that shows the CO2 emissions per capita versus GDP per capita. Basically, we have a two-tier system. On the side where we have a very high GDP, largely speaking in the global north, we have countries that emit way too much CO2 and that have abundant access to energy. On the other hand, we have the poor countries and the developing nations, quite often in the global south, that live in energy poverty. When we talk about energy poverty, there are about 3 billion people who do not have access to any form of reliable, sustainable, affordable, and secure energy. And what's estimated that every year about 4 million people die because of the lack of access to energy, because they have to burn very basic kerosene or biofuels to just have some form of access to energy. And those 4 million people, so it's more people that die because of lung issues, of burning unsustainable fuels. That's more people that die annually than HIV and malaria combined. And the countries where we have this massive energy poverty, these are the countries where we're going to see the biggest population growth. So the challenge we face is how do we going to reduce the CO2 emissions, reduce energy consumptions in the countries of the global north, while providing the right amount of affordable, sustainable, secure energy to the developing nations that are currently suffering from extreme energy poverty. There's no silver bullet. We need to sort of take any bit of resources and ingenuity and innovation available, from renewable energies, wind, solar energy, to becoming more energy efficient, to changing behaviors in the global north, to utilizing, this is what the talk is about, utilizing the subsurface in some innovative ways to store CO2, to produce geothermal energy, to use the subsurface to store hydrogen, which is becoming a very big topic in many countries, but also to continue to producing to some degree hydrocarbons, because every energy scenario of the future is predicting that some form of hydrocarbon production will continue, and specifically in the form of natural gas, which can provide countries like Tanzania, like Ethiopia, etc., with much needed access to some form of affordable and reliable energy. So why do we then care about fractures in particular? Because fractures are ubiquitous in the subsurface. They often create preferential flow paths that cause early breakthrough and bypass large reservoir volumes. So quite often we leave the things we want to produce, geothermal heat or hydrocarbons, or the things we want to store, CO2, behind. Fractures, and I quote here Brian Berkowitz in his excellent review paper from I think it was in 2002 that he wrote this. Fractures also do not possess an homogenization scale, so that strictly speaking, REV cannot be defined. So if you want to build reservoir models to simulate fluid flow through fractured reservoirs, and you see an example at the bottom right here, and the challenge that we face is how do we calculate effective properties for the fractures, for the rock matrix, such that we can reliably make predictions about fluid flow of heat, of water, of CO2, hydrogen, or hydrocarbons in the subsurface. Because the things you want to know from a fractured reservoir is when and where do fractures impact flow. You may have fractures that do very little to change reservoir dynamics. They just enhance the permeability a little bit, but they don't influence reservoir flow in any important way. In other cases, fractures really dominate the flow behavior. You want to know what the effective properties of the fractures and rock matrix are, so we can represent them in our reservoir models in a reliable and geologically realistic way. You want to know how much energy, for example, heat, is left behind the rock matrix, or how much fluids, for example, CO2, we can store in the rock matrix. And ultimately, we want to know how we can engineer the reservoirs to minimize risk. We can't change the geology of the reservoir, that's a given. We can do some clever well placements, injection production strategies to minimize the risk, for example, of early water breakthrough in geothermal reservoir, or ensuring that we can store the right amount of CO2, the target volumes of CO2 in a subsurface storage site. But when we do this, we face a number of challenges. And the first one is the uncertainty in the fracture properties itself. And what you see here is a picture from Mark Bentley, colleagues who attend Watt University and also works at Trax, who does a fantastic field trip in the south of France. Runs a fantastic field trip in the south of France. I can only recommend you to attend. And what you see in these pictures are fracture patterns that are observed on the coastline in the south of France along sort of an hour-long boat trip. So space of about a few kilometers, typical subsurface reservoir. The top line, on the top, you see the actual fracture outcrops. On the bottom, you see the interpretation, the fracture geometries that are present in the outcrop. And we see widely varying types of fracture patterns in the subsurface over a relatively short distance in space. On the bottom left, we have some through-going vertical joints. The fractures are always in red. The bed boundaries between individual sedimentary layers are in blue. So these big through-going vertical fractures that are relatively poorly connected, that are probably going to enhance the background reservoir permeability, but they're not going to dominate flow. So this would be something we're trying to think about, how we can group the fracture permeability and matrix permeability together. Then the second picture from the left, we have bed-limited joints. So the fractures in red terminate against bed boundaries. The fractures are much better connected. And we have some very high matrix blocks and very small matrix blocks. So this would be something we may be thinking about modeling it as a dual continuous system. We model the flow in the fracture domain separately from the flow in the rock matrix. The rock matrix provides storage. The fractures provide flow in a dual continuous, dual porosity concept. On the two pictures on the right, we have fracture swarms. So we have and faults. So we have a concentration of fractures in a very narrow space, in a very narrow interval. These would be things where we may be thinking about modeling them with as discrete features using tools like, or approaches like the embedded discrete fracture models, XFEMs, etc. Things that Luca is working on, Anna Scotti, who I saw in the audience, are working on. We use some of these novel mathematical discretization techniques to represent fractures in the reservoir model. The next problem we face is how do the fractures and matrix exchange fluids, and what's the impact of wettability, and what kind of mathematical models do we want to use here? So we have this picture here with these bed-limited fractures, and we can consider sort of two exchange mechanisms that we see very often in subsurface reservoirs. So you have the rock matrix in red that could be filled with oil or water, so oil in hydrocarbon system, water if you want to store CO2. This rock matrix in red, and that's surrounded by either fractures filled with water in blue, and we have inhibition driven by capillary forces largely, or fractures filled with gas. It could be hydrocarbon gas, it could be CO2. We have gravity drainage in these tall vertical matrix blocks. And what we do know from experiments and mathematical theories that have been developed is the amount of recoverable fluid as a function of time really strongly depends on the wettability of the fluid that is present in the rock matrix. And the recovery R is typically some complex nonlinear function of the permeability, the viscosity, relative permeability, and capillary pressure. So you need some way to describe these functions. The third challenge that we face geomechanics, because as we're producing reservoirs, we're injecting fluids, producing fluids, and the reservoir pressure changes, fractures can open or close, and as we open and close individual fractures, the hydraulic connectivity of the fracture network can change. Small changes in fracture apertures can have quite significant impact on fracture permeability. We see as a study by Obiscaret and others that we didn't do, but it sort of we weren't involved in this, but it shows very nicely the impact of geomechanics on flow in fractured reservoirs. So you have the same fracture network geometry, and then different stresses, stress orientations applied to the fracture geometry. And if you carefully I hope you can see my pointer, if you carefully eyeball so the top row and the second row, you can see how the water saturation that's being injected into that fracture geometry, how that water saturation changes quite significantly depending, like from the top row to the bottom row, for the same fracture network geometry, simply as a function of different stress state. We see this more dramatically here if we compare the produced oil as a function of pore volumes of water injected, that as the stress state changes for the same fracture geometry as the different fractures open and close, we get very different production behaviors. And we want to, and what has been so realized over the last decade or so, that geomechanics of naturally fractured reservoirs can be very complex and have a key control on the reservoir dynamics. But the interesting part is it's not just geomechanics of the fractures themselves, but also the rock matrix that has fundamental impact on how the reservoir behaves. This is work that Amir Hagi did together with Rick Chalaturnik, another energy simulation chair at the University of Alberta in Edmonton. And I had the pleasure of working with Amir and Rick for a couple of years. And Amir published some really interesting, really excellent papers where he showed how the impact of geomechanics or how geomechanics impact the way fractures and rock matrix exchange fluids. So what you see is the normalized volume of imbibed fluid as a function of time for the same rock that has been exposed to different confining pressures from 1 MPa to 30 MPa. So this is experimental data. And what we see is the rock is being squeezed, that the amount of imbibition, the amount of water that's imbibing the rock, displacing, in that case, a gas phase, is decreasing. So the changes in stress state in the rock matrix also have a fundamental impact of how the rock matrix and the fractures interact. And the reason for this is that as we stress the rock, as we increase the confining pressure, the permeability decreases. That's shown here in blue. That's sort of intuitive. But also what's slightly less intuitive, perhaps initially, is that the irreducible water saturation, the maximum water saturation, so the relative permeability curves, the endpoints of the relative permeability curves, have ever so slight changes. And because imbibition is a function of permeability, relative permeability, capillary pressures, these changes in permeability, the changes in relative permeability endpoints, have quite substantial impact on the strength of imbibition, the rate at which rock matrix and fluids exchange. Rock matrix and fractures exchange fluids. So if we want to study our favorite geoenergy reservoir, it doesn't matter if it's geothermal energy or CO2 storage site or hydrocarbon site, well, of course, we can run some very complex simulations, fully coupled simulations that couple geomechanics with hydrodynamics. And there are various numerical approaches to do this, and the community has worked quite extensively on them to accelerate them and get the geomechanics coupled in a computationally effective way to the hydromechanics. So we can build our reservoir models to simulate flow, and we embed them in a geomechanical model. We simulate the deformation, and we can do some uncertainty quantification approach where we think about all the different types of uncertainty that we could counter in a reservoir to try to understand how a fractured reservoir could behave during production. This is feasible, and but it becomes possible, but it becomes very quickly infeasible because we have a large uncertainty space, and these simulations, despite our best efforts, take an awful amount of computational time. So the approach that we have and the idea of the talk is to think a little bit how we can explore uncertainties in a faster way, to have a little bit of a pre-screening exercise that allows us to zoom into scenarios, into parameter space that really matter. So we're not replacing the complex simulations, but we try to focus on those simulations that really matter. So we use the CPU time or computational efforts in the most, in a very wise manner. So the approach that we follow is we use some analytical solutions to quantify fracture matrix transfer. We then use digital rock physics, so this is Masha's world, to understand the changes in relative permeability curves and capillary pressure curves and feed them back into these analytical solutions. We use flow diagnostics, something that Knut-Andreas Lee and his group at Syntev have really pioneered, and I think I saw Mike King in the audience as well. So Mike King has done this very nicely on streamline reservoir simulation as well, to compare and contrast different reservoir behaviors. And then we've enhanced the flow diagnostic framework by pore mechanical simulations to understand how pore mechanics deformation could impact reservoir flow. Eventually wrap this all up into a screening framework to identify first order parameters. I'm going to walk you very quickly through those individual steps in the remainder of the talk. So the analytical solutions for fracture matrix fluid exchange, this is work that Karen Schmidt has done over 10 years now, again, when she was a PhD student with me, and Raphael March has continued that work to look at sort of early and late time behaviors. And the idea is that we come up with an analytical solution to model imbibition and gravity drainage processes in fractured porous media. And the fundamental concept is very simple. We look at the recovery, and that's equal to the maximum recovery for a given rock fluid system, times 1 minus the exponent of rate transfer coefficient and time. And this rate transfer coefficient beta, that encapsulates the permeability, the fluid properties, the relative permeability, and the capillary pressure curves. And what Karen and Raphael have shown, that we can come up with analytical solutions that match experimental data and reference solutions very exactly. Because we're SIAM, normally I don't show this slide because it gets mathematically, gets a little bit mathematical for most audience. But because we're SIAM, I'm going to show that slide here. So for imbibition, the analytical solution is actually quite trivial once you come up, or once Karen came up with the fundamental idea. So use essentially an analog to the Buckley-Leverett solution. So what we do is we say, what's the total volume of water or fluid that has imbibed the rock, QW, and we calculate this by integrating the rate at which water is imbibing the rock. That is given, that imbibition rate is given by the capillary pressure and the viscosity and the permeability, the relative permeability curve. So integrate over the rate at which fluids imbibe, and that is equal to 2 times a constant c and the square root of time. The constant c is not some arbitrary fitting parameter, but is something that can be calculated exactly for every given fluid rock combination. How we do this, we define a similarity variable for a diffusive process. You see here some experimental data where water saturation is a function of the similarity variable for an imbibition front, and everything collapses to a single curve. And then we use an analogy to the Buckley-Leverett solution. We take the fractional flow, the derivative of the fractional flow curve for not advection-dominated transport, but in this case for capillary-dominated transport, and calculate 2 times this constant c and the porosity here, and we can solve that equation for a given fluid rock system quite effectively using Python, MATLAB, or even a simple Excel spreadsheet. Once we've calculated that constant c, we can back calculate what this total at any given point in time, what the total volume of imbibed fluid is. And then we simply say, well, what's the total volume of imbibed fluid divided by the total volume of that is available for in the rock space. And that gives us our non-dimensional time, and that non-dimensional time is equal to real time times that rate transfer coefficient beta. And then we have our simple Aronofsky model that gives us the recovery at any given point in time for an ultimate recovery for this transfer function. I'll come back to that beta, so for that rate transfer coefficient, I'll come back to that beta over and over in the talk. And because that analytical solution is very simple to calculate, then what we can do, and this is again Amir's work here, what we can then do is take different relative permeability, capillary pressure curves, permeability curves, porosity curves for different stress states, and calculate, solve that analytical solution to model what is the recovery as a function of time for different effective stresses in our rock matrix, and see how recovery changes as we're increasing or decreasing the confining stress in our reservoir. It gives us sort of first order look to understand how important are geomechanical effects on fracture matrix transfer. Now, where do we get these relative permeability and capillary pressures from? This is where Masha's world comes into play. We can do, of course, laboratory experiments, but they can take quite a bit of time. So we can do instead digital rock physics, where we scan a core, we extract the pore network, we run some pore scale simulations to get approximate relative permeability capillary pressure curves. We then stress the rock in the laboratory, scan it again, extract a second pore network from the stressed rock, rerun our reservoir or pore network simulations to see what changes we get, what approximate changes we get in terms of relative permeability capillary pressure curves, and then calculate the volume of imbibed fluids as a function of time for different effective stresses, and the effective stresses then influence that parameter C that that essentially describes the strength of imbibition. So it allows us, it gives us a framework where we can have a very quick look to understand how strong a gravity drainage imbibition in a fracture porous media, meaning how fast do the fractures in the rock matrix exchange fluids. It's not the final answer, it's a very first quick look, and then also evaluate if the reservoir is deforming, the reservoir is under stress, how much does that deformation of the rock matrix impact the fracture matrix fluid exchange rates. Next step then is to think, well, what is actually happening in terms of fluid flow in the fractures themselves, and this is where the flow diagnostics come into play, and this is a set work that Knut-Andreas-Lie and his team at SINTEF have really pioneered, and other people like Mike King have also worked on this quite extensively in the context of streamlined reservoir simulation. Fundamental idea is very easy. We simplify the physics to get do some very quick simulations that only take seconds and give us an idea of how the reservoir could behave. And the fundamental property in flow diagnostics is the time of flight tau, which essentially tells us how long does it take a virtual particle to travel from injection well to any given point in the reservoir, or from that given point in the reservoir to any given point from any given point in the reservoir to a production well. We sum up the forward time of flight and this backward time of flight, we get the residence time. We can visualize the residence time on the reservoir grid. And if we have short residence times shown here in blue, that means these are areas where the fluids are being swept very effectively. And we have slow residence times shown here in yellow. These are areas of the reservoir where fluid flow is that are not effectively swept. And what Knut-Andreas has demonstrated that we can use the streamline-based calculations of the time of flight, so that's Mike King's world, to do the same calculation in a very effective way directly on the reservoir grid using finite volume techniques, and he has very kindly made everything available through the MATLAB reservoir simulation toolbox as an open source code. What Andreas and his team have also shown is that through some additional tricks, we can then work out directly on the reservoir model grid how the reservoir is partitioned, so we can identify injector-producer pairs and influence regions within the reservoirs, regions where a certain injector-producer dominate the reservoir by dynamics. Again, the same can be done streamlined, but Knut-Andreas and his team have demonstrated how we can do this directly on the reservoir grid as well. And last but not least, what Knut-Andreas and his team have shown is how we can derive some dynamic properties, for example, Lorentz coefficients that tell us how heterogeneous is the flow field itself. So some dynamic quantities that allow us to characterize the heterogeneity of the fluid flow within the reservoir. And this is work from Francesca Watson, who is a researcher in Knut-Andreas' team, and she actually was a postdoc with us as well. And what Francesca has shown here is that for an ensemble of reservoir models, we can use things like sweep efficiency and this Lorentz coefficient that defines the heterogeneity of the flow field to screen an entire reservoir model and cluster an ensemble of reservoir models and cluster that ensemble of reservoir models to identify representative reservoir models that capture the overall flow behavior. So here we have many dozens of individual reservoir models shown by these individual gray dots, and a small number of reservoir models could be identified through screening and clustering that capture the full range of uncertainties, the full range of reservoir behaviors that is inherent to that big reservoir model ensemble of many, many dozen, over 100 individual ensemble members. We can describe the full range of reservoir model behaviors by essentially 4 individual reservoir models that capture the broad spectrum of reservoir dynamics. And we can do this using flow diagnostics. We can screen, rank, and cluster individual reservoir model ensembles in the matter of minutes. Now, if you do have a fractured reservoir where the fractures only enhance the matrix permeability, where they dominate the reservoir permeability, you can use flow diagnostics straight out of the box in MRST to do these clustering exercises. And Daniel Wong, who was a PhD student with us, he did a very nice PhD thesis where he actually worked out how we can how we can distinguish when the fractures dominate fluid flow and when they can be lumped together with a rock matrix in a single porosity concept by essentially mapping out using effective medium theory where do we have a region of single porosity flow and where we start to transition to dual porosity behavior. If you do not have a single porosity behavior, so the fractures really start to dominate reservoir flow, and flow in the fractures is at a significantly different time scale compared to fluid flow in the rock matrix, then we need to enhance our flow diagnostics. And that was work that Victoria Spooner did during her PhD. And she came up with the idea of a dual porosity Damm-Köhler number. The idea is what we simply do is we have the rock matrix and the fractures, and we want to know how fast does the rock matrix, for example, release its oil, or how fast does the water in the fracture imbibe the rock matrix, and how fast is that exchange of fluids between rock matrix and fracture compared to the flow rate in the fracture itself. That Damm-Köhler number, the dual porosity Damm-Köhler number, simply compares the transfer flux, which is our beta, this rate and transfer rate coefficient, with advective flux in the fractures, the Q, which we get from our flow diagnostics. So if we do have a reservoir model, and this is a real reservoir model here, and we have the fracture permeability for each matrix block, or each grid cell, we can calculate what the transfer rate coefficient is, beta. First thing we can do is we can then use the beta, bin them, and look at what is the recovery as a function of time. The thicker the line is, the more, that means the more cells have a beta value in that range. So what we see for that particular reservoir, there's a large number of cells that have a beta value of sort of 10 to the minus 6. And if we follow that curve, that tells us that we get sort of good recoveries after several hundreds of days. So that means that a significant portion of the reservoir can release its fluid from the rock matrix into the fractures over the lifetime of the reservoir. The next thing then, what we can do is we can calculate this Damm-Köhler number on a grid block by grid block basis, for example, and identify regions where we have high Damm-Köhler numbers and low Damm-Köhler numbers. High Damm-Köhler numbers means that the rock matrix is able to release its fluid very effectively. So there is strong exchange between rock matrix and fractures. And low Damm-Köhler numbers mean that fracture advective flow in the fracture is much stronger than the transfer between fractures and rock matrix. And these are regions where we are perhaps at risk of early water breakthrough in a hydrocarbon system, or where the CO2 may simply disappear and is never being taken up within the rock matrix, if you think about a CO2 storage site. So these enhanced dual porosity flow diagnostics really allow us effectively to screen uncertainties in a reservoir models based on fracture properties and the rock matrix properties of a very wide range of reservoir parameters, very broad uncertainty space, and get an idea of how the reservoir behaves before we start running actual simulations. And as I said, no, we wouldn't have been able to do the work without SINTEF and without Knut Andreas Lee and his team and Olaf Moyner and Stein Krogstad and Francesca Watson and all the other great members who have developed the MATLAB reservoir simulation toolbox. And we have done our best to implement everything in MRST and make the work available as open source through MRST. So now what we have is two things. We have a tool that allows us to approximate the strength of imbibition and gravity drainage, so the strength of fracture matrix fluid exchange as a function of the fluid properties, the rock properties, and the effective stresses in the reservoir. We have these enhanced flow diagnostics that allow us to understand how the fluids flow through the fracture network and how that or the flow rates in the fracture network in combination with the fracture matrix fluid exchange could create areas where we can get early water breakthrough, early gas breakthrough in our reservoirs. Next step then is to think about, well, what is going to happen geomechanically when we're starting to producing our reservoir. I should provide as a caveat, we're only looking at linear polar elastic theory so far, and this is work that Leslie Gutierrez-Sosa, PhD student, has recently completed her PhD thesis, has worked on. The idea is very simple. We take a pressure solver to get the pressure distribution for some well controls in a reservoir. We then have a mechanical solver that calculates for the displacement, compute the stresses and strain. We update the permeability as a function of stresses and strain. We run the pressure solver again until we get convergence between the mechanical solver and the pressure solver. Once everything is converged, we get we get the permeability, pressures, displacement, stresses, and strain. We get the velocity calculations. We can do our flow diagnostics, simulations or calculations as a post-processing step. These simulations only take a few minutes, no longer seconds, a few minutes, because we have the additional complexity of the mechanical solver here, and we use the virtual element method in MRST for this. And again, it's not going to meant to displace a full physics simulation. A transient simulation is meant to simply look very quickly how bad could the situation be if geomechanical effects are present in our reservoir. So the framework for screening geomechanical uncertainties is quite simple. We have our reservoir model, one ensemble of reservoir model. We do the hydrodynamic pore mechanical coupling, where we have a pressure solver on a geomechanical solver. Once everything is converged, we run the flow diagnostics, screen our models. The flow diagnostics show that we get fundamental different flow behaviors when we consider pore mechanics. Then this means we need to study full physics, run full physics simulation, we couple pore mechanical and hydromechanical simulations. If the simulations show that there's no difference between the flow diagnostics when we consider pore mechanics, then we can continue with conventional flow simulations. If you have a dual continuous, again, if the fractures only enhance permeabilities, we can sort of use that straight out of the box. And if you have a dual continuous system, so different timescales of fluid flow in the fractures in the rock matrix, we can use and treat the rock matrix and the fractures as a composite medium. And I'm not going to walk you through those equations. I thought we'd just throw in a few equations here to because it is a SIAM talk. So Leslie has worked out all the mathematics for dealing with a dual continuous system if you want to do pore mechanical simulations. And the important bit is what Leslie also did is she coded her environment in a way that we can replace they can use different conception models that relate, for example, aperture change to permeability changes, because there's a lot of discussion in the literature. And the key uncertainty is which conceptual model should we use to update the fracture aperture as a function of stress and then translate that aperture change into a permeability change, for example. Here's an application that Leslie has done for the so-called Amelago model, which is a geologically reasonably realistic reservoir model, a fractured carbonate reservoir model. We have 4 injectors and 1 producers here. We have a number of rock types, a number of different carbonate facies with quite a range of permeability values, quite a range of porosity values. This is the matrix permeability, matrix porosity. Leslie then assigned a Young's modulus to the rock matrix. See the values here. We have a uniform Young's modulus for the fractures, and we have the composite Young's modulus. Then she ran this framework to understand how do the pore mechanics influence the reservoir dynamics using flow diagnostics. And at first look, nothing much happens. So we have permeability distribution on the left-hand side for the matrix, for the fractures, on the right-hand side for the matrix. Red is model without pore mechanics, blue is a model with pore mechanics. We see a small shift in fracture permeabilities towards small shift in fracture permeabilities and a small shift in the matrix permeabilities. If we zoom in, however, we see so that this blue bar where we have zero fracture permeability, zero matrix permeability increases the moment we start considering realistic pore mechanics for the Amalago model. And these very subtle changes in fracture and matrix permeability change the reservoir connectivity quite a lot. So what we see now is on a layer by layer basis, the cumulative flow in the reservoir. The blue curves are the with pore mechanics, and the red bit then is the additional flow that we get if you ignore pore mechanics. And what we see is that if we were to ignore pore mechanics in this particular reservoir model, we would anticipate much higher flow rates. We would anticipate, for example, we could store significantly more CO2. We can get much faster flow of cold water in a geothermal. If we were to inject cold water in a fractured geothermal reservoir, we would anticipate much faster flow rates of the cold water through that fractured reservoir. The other interesting thing is also what we see is how the reservoir regions where injector and producer pairs interact change. Again, blue with pore mechanics, red without pore mechanics. Generally, we see reduction in volumes, in reservoir volumes, where injector and producer pairs interact if you consider pore mechanics, because a larger part of the reservoir has zero permeability now, and we have no flow and no sweep in those parts of the reservoir. The other very interesting thing is, if you run through this exercise, what happens to the strength of the fracture matrix exchange. So if you go back to Amia's work, we looked at how we can update these analytical solutions by considering geomechanics. Leslie then recalculated for the beta, this transfer rate coefficient, for the given stress state using Amia's correlations. And what we see is that initially we get sort of a relatively well-defined transfer rate for the Amalago model, and that becomes much more heterogeneous, much lower the moment we start, much more heterogeneous, some case higher, in some case lower, if we start to consider pore mechanics in the reservoir. So the strength of this fracture matrix exchange is going to be fundamentally different if we consider pore mechanics in the reservoir. So although the permeability hardly changes, the reservoir dynamics are going to be greatly affected the moment we start considering pore mechanics for the Amalago model. So this would be a very strong indicator that we need to do much better, that we need to run much more complex full physics reservoir simulations. What Leslie then did is she wrapped this all up into an uncertainty quantification framework to screen parameters. So we have our reservoir model here, number of different uncertain parameters, from boundary conditions to conceptual models to reservoir parameters, experimental design. She trained, she used the flow diagnostics then to create a training data set for a machine learning algorithm. So in this case, an ANN-based proxy model. And then that proxy model she could use to do some sensitivity analysis and look at parameter combinations to identify some representative models that we want to consider possibly for more detailed reservoir simulations. Here again are some results for the Amalago model. What is very interesting to observe is that a lot of the things we can measure in the laboratory, at least for the Amalago model, things like the Young's modulus, fracture for the fractures in the rock matrix, have very little impact on the sweep efficiency, while the boundary conditions, so the stress state, and the way we think about permeability changes assume isostress or isostrain and the different correlations that we could use, they have a much stronger impact on the reservoir dynamics. What Leslie could also show is that we can then use clustering to group or identify certain representative behaviors of the reservoir dynamics for the Amalago model. So each of these different colors represents one specific behavior or cluster of behaviors that is representative in terms of the reservoir dynamics for the Amalago model. And that big red dot is the one single case we would ignore geomechanics. And then what we see here is the production rate as a number of pore volume, as a function of pore volume injected for the Amalago model for these different representative models from the individual clusters. We see that we do a reasonably good job, not a perfect job, to capturing the spread in the possible production behaviors for the Amalago model by reducing the hundreds of different individual parameter combinations. We can reduce them to 5 representative parameter combinations that capture the reservoir behavior, the spread of possible reservoir behaviors in a reasonable way. But all these behaviors are substantially different from the situation where we had to ignore poromechanics, which is that single red curve here. So what we have now is a framework. We can look at the fracture matrix fluid exchange, can use the flow diagnostics to look at how fluid flow happens in the fractures and how fracture matrix exchange is being impacted, how the flow in the fractures interacts with the fracture matrix exchange. We can enhance these flow diagnostics using geomechanical, poromechanical simulations to understand how the matrix properties and the fracture properties change. If we put stress on the reservoir and we do see fundamental changes, we can even, because the calculations are very fast, we can even do some initial parameter screening to identify certain parameter combinations, certain clusters of behaviors that we may want to focus on in more detail when we run complex simulations. So this is not all theoretical. The question is how we can actually work with real data to get an idea on which of these curves are we. And I'm going to spend the last 5 minutes of the talk to present some first ideas. The question is, what can we actually see in real data to guide us in which of these individual behaviors and which of these clusters we could possibly be in? And the idea here is, and this is work that Alfredo Freitas, a PhD student, David Agia, Patrick Corbett and I did over many years, is to use this concept of geological well testing, where we use data from outcrop analogs, image logs to build a fracture network model. And these would be situations where we represent the fractures explicitly using all the nice numerical techniques that SIAM is working on, that Luca and others, Anna, are working on, for example. And then we create a synthetic pressure response. We compare that synthetic pressure response to the well test. Good agreement, we get an idea of what the fracture properties could be. If we get poor agreement, we can adapt our fracture properties, run the simulations again to learn about what the key fracture properties could be. What Alfredo has shown, and David as well, is that if we actually look at real data here in dots and we do this approach and simulate these well test curves, the dashed curves, then we can actually learn a lot about the key fracture properties in a real reservoir. So here, this is data from a real reservoir, and we could get an initial idea about the fracture spacing and the distance between the fractures and the well. And the question we ask ourselves is, if we would have a very large training data set, could we actually detect fracture properties systematically using well test data? So Alfredo set out and tackled this challenge, and he created a synthetic training data set where he looked at probability distributions for fracture length and fracture densities, and he created a training data set of over 2,500 different but geologically constrained fracture networks. And you see some of the fracture networks, 3 example fracture networks here in the bottom, where the different colors indicate different orientations. And for each of these 2,500 fracture network geometries, he simulated a pressure transient signal, and you see 2 examples here, one where the well is located in the rock matrix, one where the well is intersecting a fracture, and then use that training data set with these 2,560 over 2,500 synthetic drawdown curves to train as an input for machine learning algorithm to try and cluster and rank and compare the individual pressure transient signals. When he did this work, he found out that there's 12 different clusters of pressure transient signals, and each cluster represents a certain type of reservoir behavior. So you see the different clusters and the different pressure transient signals here on the right-hand side, and here are some silhouette plots that show you that we actually come up that 12 is a reasonable number of clusters to capture the diversity of flow behaviors. And the interesting part is, if you use the multidimensional scaling, is that you start seeing some certain behaviors. So of these 12 clusters, clusters 10, 11, and 12 sort of lie outside significantly different compared to clusters 1 to 9. And this is because in clusters 1 to 9, the well is actually not intercepting a fracture. Clusters 10 to 12, the well intersects a fracture. And what Alfredo then did is to try and link back the geological features, the fracture network characteristics that are inherent to these 12 individual clusters to the cluster behavior. And he looked at things like the average fracture length, fracture apertures, fracture intensity, distance from wellbore to the closest fracture, and fracture connectivity. What Alfredo found out is that within these 12 individual clusters, we get a much richer response compared to classical analytical methods to interpret well test data for fractured reservoirs. And very interestingly, these 12 clusters always relate to a consistent grouping and trends in fracture properties. What we've learned is that the main control is always how close the well is actually located to the nearest fracture. And secondary controls are fracture intensity and connectivity that relate to those 12 clusters. Average fracture apertures are not important for the ranges considered. And so far, this is sort of more of a proof of concept. Alfredo is continuing to work to expand that. Is doing additional research is needed to consider a wider range of fracture geometries and actually compare it to some real data. And although some of the fracture network geometries are relatively simplified, when you start actually looking at real data, what we see is that the individual clusters actually match data very well. And we get some really well-constrained really good ideas, well-constrained ideas of what the fracture properties could be in a reservoir using this machine learning enabled classification approach. So we're now going full circle. We have a method where workflow we can look at the fracture matrix exchange. We can get the flow diagnostics to understand how the flow in the fracture interacts with the fracture matrix exchange. We can look at how the fracture reacts to deformation, the rock matrix react to deformation. Does that impact flow behavior? We can do an uncertainty quantification framework using these enhanced flow diagnostics to understand how what are the key parameter sensitivities that could control reservoir behavior. And with this first step of this classification approach, we can now actually hone in on certain representative behaviors, because using subsurface data, we get an idea which clusters in our uncertainty quantification framework are more realistic or more likely or less likely related to the subsurface properties that may be present in the reservoir. So to sum up, what we do have a framework, we're working on is a framework to analyze uncertainties in fractured reservoirs. We use the digital rock physics to get an idea about how permeability, porosity, well perms, and capillary pressures can change. We have analytical solutions to quantify fracture matrix interactions, including how these interactions change as a function of effective stresses in the reservoir. You can use flow diagnostics to approximate changes in the reservoir dynamics. This is really the work from notoriously, and we've enhanced this a little bit to consider the impact of poromechanics and extended them to consider dual continuous systems. Because these calculations are so fast, we can then run a large number of simulations to screen and cluster reservoir models and identify some of the key parameters, key reservoir behaviors that we need to look out for. And by creating training data sets, in this case for well tests, we can potentially start to detect the key parameters in real data, the key fracture parameters in the real data, such that we know which of these clusters are more likely and less likely to represent the reservoir behavior. And again, the aim is just to accelerate and not replace the reservoir characterization, the reservoir modeling and simulation workflows that SIAM and the SIAM community is working on, because we still need them at the end of the day to consider the full physics. We still need to get better algorithm, better numerical methods to accelerate these, or to make these simulations computationally more effective. But what we want to help is to spend our efforts and the CPU time where it matters most. But the research is far from over, so we need to do much more work in the classification scheme. We're just starting to scratch the surface on the well testing work. There's much more work needed to be done in the pore mechanics. For example, we're only considering linear elasticity, so plasticity. We may want to consider the entire business of induced seismicity. We haven't even started touching. I know Mike King and others, they have worked on much more elegant formulation of fracture matrix fluid exchange than we have done that we could consider. There's a lot of additional work that we can use to bring together to really understand fractured reservoirs better and run our simulations in a more effective way. With that, thank you very much for your attention. Again, thank you to all the PhD students who have done the lion's share of this research, and it was, as I said, my honor, my pleasure to represent their work. And I do hope I haven't bored you to death, and that there are maybe even some questions at the end of the talk that I'm happy to answer.
Thank you. Very impressive talk. And indeed, it's time for questions. The only thing that I am not able to unmute the participants, apparently. I don't know why, because in principle, I should have something to mute them. So what we can do, we can try to look at the question and answer, and I will just, okay, there is at the moment only, thank you for the interesting presentation, but
thank you.
We're waiting for.
Can I abuse my panelists?
So maybe you're able. You
the fact that I can unmute myself.
Oh yeah, so, of course you can unmute yourself. That's for sure.
I have a question that I think would be on a behalf of a student coming into the world of fractured reservoirs. So if I were a starting student, where would you, and I don't necessarily sign up with the group that gives me the research topic. Which topic do you think is sort of the most burning part of this workflow? Because this workflow has the dizzying number of topics all together.
I would argue the geomechanics side, and that's because I understand very little about reservoir geomechanics, so I'm really relying on others there. But I think this is something how we either simulate geomechanics more effectively, how we consider more complex, not just linear elasticity, but plasticity as well. These effects, I think this is still an open field of research, and that would be my advice to go for.
All right.
Sorry, Marsha.
Yes, thank you. So I will let
okay. We have a question from the Q&A. You from Ron Sawartzi. I hope I'm pronouncing the name. You didn't mention thermal effects. Could they be embedded explicitly in your framework, or would there be significant challenges?
So thermal effects, I think it's possible. And indeed, there's a PhD student at Florian Doster, and who was a co-author on many of those papers, I should mention. Now I supervise and to include thermal effects into flow diagnostics framework. And there are some scaling groups that you can use to calculate how thermal fronts move through your reservoir under advective dominated flow. The challenge with thermal effects is that you also have heat conduction, which can be very strong. And some ideas we have for the PhD student to look at is, again, Mike King's wonderful work on diffusive time of flights to approximate diffusive effects, conductive effects in a reservoir, or potentially some other ways, efficient ways to try to simulate thermal conduction in the reservoir, because we can't just look at advective transport. In terms of the reservoir geomechanics, there I said, no, I'm not a geomechanicist. There I really haven't thought about how thermal stresses could impact the mechanical behavior of the reservoir. So that's maybe what Masha said, a really nice way to for a talented graduate student to find new effective ways to model them, include them in sort of an uncertainty quantification framework.
I have two questions. One is concerned the possibility of the fracture to be completely closed due to the pyromechanics effect. Do you take that into account? I mean,
so,
the permeability can go to zero. I mean, the fracture can be completely closed by the action of the stresses.
So yes, we do take this into account, but mainly because we do this very simplistically in sort of effective porous medium approach, where grid cell does have the effective porosity, the effective permeability that represents a fracture in a dual continuous system, or if it's a lumped approach where we have an effective permeability for both fracture and rock matrix. If we were to use things like EDFM, XFEM, etc., to represent fractures explicitly, so things like fracture corridors, fracture swarms, then yeah, we haven't done this, but then you would need some more advanced numerical techniques like the ones you're working on, Luca, to ensure that you get zero permeabilities and the of the fractures when they close due to mechanical effects. So we're taking a shortcut there because we work with standard reservoir grids rather than representing fractures more elegantly using advanced numerical techniques.
Thank you. Ron Savaksky, thank you for the answer. And we have another short question by Kwok.ha. I have only one small question. Do you consider the effect of fracture stiffness, Kn, in the matrix fracture mass transfer?
No, so the transfer at the moment, these analytical solutions, they only consider the changes in the rock matrix itself, not the stiffness of the fracture, because that's the rock matrix, the capillary pressure, the relative permeability, and the permeability of the rock matrix that is driving that exchange rate.
Another question is popping up. Very interesting talks, thanks, by Luis Salo. I wanted to ask about the usage of rock curves obtained from pore network simulations in your framework for fracture matrix fluid exchange. Is any upscaling necessary to go from the core scale to the reservoir scale?
Well, this, I think Masha is maybe the much better person to answer this, but the idea is, so if we're staying essentially at the moment, we're sort of keeping at the experimental scale, so the plug scale, and we're sort of making that huge leap of faith that whatever we get in digital rock physics is representative of what we would be modeling, measuring in a laboratory experiment. If you think about a real system, real reservoir with real heterogeneity, then yes, we would need to go and think about some much smarter upscaling than what we're doing at the moment. So yes, we need to do upscaling, but we don't do it because we're sort of hoping that what we do in digital rock physics is representative of what we were to measure in the lab, and as a quick first look. But
Well
Masha,
said. I have nothing more to add. I mean,
Okay.
all of the small scale, I think more philosophically, all of the work we do most often assumes some level of representative elementary volume being present. And unfortunately, as pointed out at the very beginning of this talk, the moment you have fractures, that theoretical framework is out of the out of the picture. So it's a level of trust that we have in all of the models to be able to connect. But any smaller scale assumes that actually you're representative of at least of the core, or whatever block you're looking at, and that could be core scale, that could be reservoir scale. Unfortunately, we don't have.
And the idea really is we try to be approximately right, not precisely wrong. So just this quick first look to see, what is the ballpark figure that we want to zoom in when we do more experiments, more elaborate simulations in this vastly complex parameter space that we want to explore.
Yeah, huge.
As they say, all models are wrong. Some of them are useful.
Yeah,
yeah, exactly.
And build your models as simple as possible, but not simpler.
Okay, I report the thanks by Luis Salo. And now, just a curiosity, what do you think of using? I've seen that you used neural networks for the analysis, right?
Yeah.
For the uncertainty quantification step. What do you think of the attempt of using neural networks also to build the reduced models of a reservoir? If you have any idea, if you have any opinion on that, of course.
So can I clarify? So do you mean for the static model or for dynamic simulations as an proxy model?
Yeah,
I'm not an expert in this.
I can
Leslie,
throw in an opinion.
Yeah, you can throw in an opinion. So Leslie has used ANNs simply because you could plug into some existing code. So to a degree was a pragmatic decision. We have played around a little bit with proxy models using polynomial chaos expansion. I think that the risk always with the neural networks is that you can end up overfitting quite dramatically, and you can be, if you then have parameters outside your training space, all bets off how good or right or wrong the results are. But Masha, you're much better suited.
Well, I've also just played with them, but this is my general. If you ideally you'd say, oh, if you have a lot of data, you should be able to organize them well. I think that we have such over-connected phenomena that we will have to work with a combination of neural networks and all of the simulation that we have. I would trust neural networks for sort of like assessing short periods of time rather than long periods of time. So some level of, combining physics-based simulation and neural network extrapolation, which is it's extrapolation, it's fitting.
And certainly what we've seen in Alfredo's work.
Data fitting on steroids.
what we've seen in Alfredo's work was, it's not neural networks, but any sort of degree of machine learning that we throw in, you still need some human interactions to check that the results are sensible, which in Alfredo's case really surprised us that it made geological sense, that it made sense in terms of reservoir dynamics. But I wouldn't just trust it and just say, well, we just stick it into a big simulator, create a training data set, apply whatever machine learning technique, and then come up with some results, and Bob is your uncle. I would always worry that there's some artifacts that we don't have control over.
Do you have we have certainly opened up a flame here. we have a question from Masuda Karantari. For multidimensional scaling, is the algorithm performed to reduce the dimension to 3 presented in the slides? As assumed, those 3 are selected for further analysis, or is the algorithm performed as to cluster based on the 3 dimensions seen in the slides? Unfortunately, I don't know which slides.
Yes, so that was I can share my screen quickly here again.
It says, is that, okay, sorry. You've got
So it's, we
oh,
were
yeah,
talking about,
okay.
so let me just perform to reduce the dimension to 3. Yes, so if I remember correctly, but I need to cross-check this with Alfredo that you wanted to reduce the dimensionality to 3.
Okay. There is then a comment from Mike King. Can I point out the advantage of physics-informed neural network in which basic physics insight act as constraints? For example, that velocity runs down on pressure gradients. Certainly, I think that some physics insights is necessary, even in this case, for sure. That's at least my opinion. And then Masood Kalantari asked, and in addition, how is the quality control performed for ANNs to make sure the ANN learn the right physics?
So that we did. So some
I
very
think
standard.
it's just a comment on what we were
Yeah,
discussing.
and we just did in that case. So we did some recursive testing. So we trained the data, then had a validation data set, and we checked, and then where there were mismatches, we ran additional training simulations.
Okay, I think we have taken a lot of your time. It was very nice.
My pleasure.